ME350 example problem for steady one-dimensional conduction without heat generation. A sheet of insulation is to be used to reduce the amount of heat loss from a warm room to the outside through a large plain wall. The inner surface of the insulation is at a temperature of 25 degrees Celsius. The air on the outside of the insulation is at a temperature of 5 degrees Celsius and has a convection coefficient of 10 watts per meter squared Kelvin, which is typical for natural convection. For Part A, sketch the expected temperature distribution in the insulation and indicate how changing thermal conductivity would affect the results. For Part B, calculate the temperature of the outer surface of the insulation and heat transfer rate per unit area by solving the heat diffusion equation directly for the two different specified thermal conductivities. For Part C, calculate the same quantities in Part B using the resistance analogy method. Our first assumption for this problem is steady state, which means that none of the properties are changing with time. Our second assumption is one-dimensional conduction in the x direction only, which is based on the information provided in the problem statement. Our third assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our fourth assumption is that there is no energy being generated in the wall, which is again based on the problem statement because it does not include any indication of internal heating. Our fifth assumption for this problem is negligible radiation for the exterior boundary. This is a reasonable assumption for an opaque wall and for lower temperatures combined with significant convection at the exterior boundary. For Part A, we want to sketch the temperature distribution in the wall. First, we draw our x-axis from 0 to L. Second, we draw our temperature axis and indicate the limiting temperatures of 25 degrees Celsius at x equals 0 and 5 degrees Celsius in the fluid away from the surface at x equals L. Next, we know that for steady one-dimensional conduction in Cartesian coordinates with no internal heat generation, the temperature distribution will be linear. Thus, we can add straight lines for the temperature for the two different conductivities, where the temperature must decrease with x by the second law of thermodynamics for heat transfer from hot to cold. Next, we indicate that the lower line corresponds to the insulation with the lower conductivity and a cooler temperature at x equals L. In the limit of perfect insulation, the temperature at x equals L will be the same as the external fluid temperature. Also, for the limiting case where the thermal conductivity goes to infinity, or a perfect conductor, the temperature will remain at the inner wall temperature of 25 degrees C. Finally, we add a curve as x increases further to indicate that the temperature decreases rapidly from the value at x equals L to the fluid temperature. We will discuss later in the course why this is correct when we cover convection. For Part B, to determine the temperature at x equals L using a standard analysis, we begin by writing the heat diffusion equation, which is a form of conservation of energy for conduction, as a partial differential equation, or PDF, in vector notation. Next, we expand the first term using the definition of the gradient and then the divergence for Cartesian coordinates. For this problem, we can reduce this equation by assuming steady state, one-dimensional conduction in the x direction, constant properties, and no internal heat generation as shown. Note that we can write this as an ordinary differential equation, or ODE, because temperature depends on only one variable, which is x. To solve for the temperature distribution, we integrate twice with respect to x to get a linear solution, as expected, with two constants of integration. To determine these constants, we need to apply our two boundary conditions. First, for the boundary at x equals L, with the fixed temperature, we get that C sub 2 is equal to T sub 1. Second, for the boundary at x equals L, With specified convection only, we use the boundary condition developed in example 1 from an energy balance at the surface at x equals L. Substituting in our temperature distribution, we solve for C sub 1 as shown. Substituting in our constants, we get our final result for our linear temperature distribution. Next, for the temperature of the wall adjacent to the fluid, we substitute in x equal to L. Finally, we calculate values for T sub 2 for our two conductivities of 10.7 degrees Celsius and 21.0 degrees Celsius. As expected, as the conductivity increases and the insulation is less effective, the outer temperature also increases. Continuing with Part B, to determine the heat transfer rate per unit area, or heat flux, we use Fourier's law, the rate equation for conduction, for just the x direction for our one-dimensional problem. Substituting in our known temperature distribution, we get an equation to solve for the heat flux, which is constant, as expected for this case where the temperature gradient is constant. Finally, we calculate values for the heat flux for our two conductivities of 57.1 watts per meter squared and 160 watts per meter squared. Again, as expected, as the conductivity increases and the insulation is less effective, more thermal energy is lost to the fluid. For Part C, we will determine the same temperatures and heat fluxes as for Part B, but using the resistance analogy. Recall that for this method, we draw an analogy between an electric circuit and a conduction analysis, where voltages are analogous to temperatures, current is analogous to heat transfer rates, and electrical resistances are analogous to thermal resistances. Also, recall that this method is valid for this problem because we are assuming steady, one-dimensional conduction with constant properties and no internal heat generation. To begin, we draw a resistance network that models our conduction problem. On the left, we have a node that represents the fixed temperature of the wall at x equals 0. Then, we have a resistor that represents the thermal resistance for the conduction through the wall, followed by a node for the temperature at x equals L. Finally, we have another resistor in series that represents the thermal resistance for the convection to the fluid, followed by a node for the temperature of the fluid away from the wall. Note that the heat transfer through this system is constant and is represented by the arrow above the resistance network. To get the total resistance for the network, we add the thermal resistances for conduction and convection because they are in series. For our analysis, since the temperatures on each side of the network are known, we begin by applying an analogy to Ohm's law to the entire circuit to solve for the heat transfer rate. This allows us to quickly solve for the heat flux, where the resulting equation is the same as for Part B. Now that we have an equation for the heat transfer rate, we apply Ohm's law to part of the circuit to obtain an equation for the intermediate temperature at x equals L. Again, this allows us to quickly solve for T sub 2, where once again the resulting equation is the same as for Part B. Note that the resistance analogy is a simple and efficient way to solve this problem. Finally, we will look at a table that summarizes the equations used to solve this problem for a plane wall. The table also includes the equations needed for cylindrical and spherical walls. For the row with the heat equation in the plane wall column, we see the version that we derived for Part B for steady, one-dimensional conduction in the x direction with no internal heat generation. For one-dimensional conduction in the radial direction for cylindrical and spherical walls, the heat equation is just a little more complicated because it accounts for the changing area with radius. All three of these ODEs are then integrated twice, and the solutions for the temperature distributions are given for the case where specified temperatures are used for the boundary conditions. Next, Fourier's law is used to determine the heat flux and the heat rate. Note that for a plane wall, the heat flux is constant, but that it decreases for cylindrical and spherical walls. This is because the area normal to the radius is increasing, Thus, by conservation of energy and for a constant heat rate, the heat flux must be decreasing. Using the resistance analogy, the thermal resistances due to conduction are also presented. The final column indicates the critical insulation radius for the cylindrical and spherical coordinates. Note that the critical insulation thickness accounts for the fact that although the thermal resistance to conduction increases with insulation thickness, the thermal resistance due to convection decreases because the surface area for convection increases. Thus, the total thermal resistance, which is the sum of the conduction and convection thermal resistances, will go through a minimum at the specified critical radius. As insulation is added below the critical radius, the total thermal resistance decreases and the heat transfer is enhanced. As insulation is added above the critical radius, the total thermal resistance increases and the heat transfer now goes down, as is typically desired when adding insulation. Finally, there are two figures included to clarify the nomenclature for the geometry for the equations in the previous table. In particular, note that for the plane wall, the area used to calculate the total heat rate is perpendicular to the heat flux in the x direction, and that the length used for the cylindrical geometry is the length of the cylinder.